And we're hearing a lot about performance-based, but I wanted to start by saying when shortly after I arrived here at Stanford in 2000, I came in 1999, but in 2000 I got the opportunity of a lifetime when Jack Maley called me up and invited me to be Deputy Director of Research for the Pacific Earthquake Engineering Research Center, whose mission was to develop performance-based earthquake engineering. And so what I'm going to do today is, and a few of the topics have been touched, which is good because I got to click through a few slides a little quicker than, but it's just touch on a few milestones in that development, because I think the performance-based framework is familiar to many of you, so I won't belabor some of those things, but just to look back on a few of the milestones, and apologies to my friends from Berkeley, these are some of the milestones that are more associated with what was going on here at Stanford, or we contributed as part of this much larger endeavor for the Peer Center. Just one of the best definitions of performance-based I come back to is a slide Jack Maley put together early in the Peer to transform earthquake engineering, where we didn't have a scientifically designed seismic hazard. We had zone maps, if you will. Indirect design approaches, prescriptive methods, elastic analysis, and then undefined uncertain outcomes. So the whole thing with performance-based is to tackle each of these, the hazard, direct design approaches, and we do a lot of nonlinear analysis to help us understand the behavior structures under extreme motions and kind of characterizing the performance and carrying through the whole thing, the probabilities, the uncertainties all the way through that process. So just thinking about things that were setting the stage, Peer started in 1997 with this mission, and it just so happened that was the year that the National Hazard and Building Code went from the old kind of zone maps to what we now know based on a probabilistic seismic hazard basis. The maximum considered earthquake appeared in the NEHR provisions and then in ASC 7, the building codes in 1997. So we're starting to get the hazard piece into that. In terms of the vision of performance, I think this is where I really credit a lot of the practitioners who work on these things. And this diagram that you see here associating different levels of performance with different return periods of earthquakes and with different types of structures, whether it's a safety critical hospital or other. And this really was laid out in SEOC Vision 2000, which was published in 1995. So these were the things that were kind of in place at the beginning of that process. Also, some projects going on at the time. Helmut Krawwinkler, there was a Sac Steel project looking at the damage to steel moment frames after the Northridge earthquake. Helmut was in charge of a team there looking at overall building performance, doing a lot of drain 2D analyses, as you see here, of these kind of case study buildings that were put together with SAC. And at the time, we were really going from a static pushover analysis to nonlinear dynamic. And in fact, the first name that these kind of IDA, incremental dynamic, had were dynamic pushover analyses, which is really just taking a ground motion, incrementing it out, but it's not a static analysis, it's a dynamic one with increasing drift. As Bill mentioned and Ann mentioned, Alan Cornell with Dimitris Van Vostikos, I mean, a lot of people were sort of doing these, but they kind of formalized the method and they looked carefully, and this is a fascinating, it has about 6,000 citations, their paper on this, so it's worth taking a look at. Looking at what happens as you increment it and how the behavior is changing. They came up with resurrecting cases, they so-called. Also, an important thing was, what do you put on the vertical axis as you increment the ground motion? How do you keep track? Is it the scale factor, peak ground acceleration, first mode spectral acceleration? These were all kind of questions at the time, things that Alan brought to the table. And then there were a whole host of questions on the legitimacy of record scaling, statistics on response parameters, and so forth that are kind of laid out in this paper, and still kind of going forward, people grappling with. But this was like early 2000. Ann mentioned the work of Keith Porter, that PhD thesis, assembly-based vulnerability of buildings, which what Peer was going to subsequently do on the FEMA P58, this very detailed set of analyses. Keith had actually outlined that in his thesis at the outset. Keith Porter, in the Peer Center, we later enlisted to actually manage some of testbed case studies that were done in the center. So Keith continued to stay involved in that. Helmut Krawwinkler with a good friend of his, Peter Pfeiffer, from Slovenia, organized a series of workshops. They became known as the Bled workshops because they were held in this lovely Lake Bled in Slovenia. You see these here. They kind of started by looking at kind of nonlinear dynamic analyses, next generation building codes, performance-based. This was a big 2004. That was, by the time Pier, a lot of the framework had come together, so a lot of discussion there. And then the last workshop in 2011, looking from performance-based to resilience. In terms of performance-based concept, Bill Holmes comes up with very clever ideas and ways to articulate those. And this was a slide he brought to the Peer Center. Thinking first generation performance-based, he mentioned the ASE 41 going back to FEMA 273, and where we were trying to go to, bringing in dynamic analyses and more explicit measures of response. So that's essentially the framework that was being developed through the Peer Center. In the process, breaking it down, going from the hazard into the structural analysis, into the damage assessment, and then into the loss assessment, kind of clearly articulating each part of the process. And when you're working with a large collaborative group, as we were in the Peer Center, is doling out different projects to different people and groups who work on different parts of that process. So having this kind of modular framework was very helpful that way. The first version of our integral equations, this was something that Alan Cornell and Helmut wrote in a Peer Center News, a double integral equation going from intensity measure to damage measure to decision variable. The damage measure was actually, they characterized, if you look at the paper, in terms of drift. Quickly, some discussions, though, we kind of were saying, well, drift is not damage. Drift causes damage. So we kind of disaggregated a little bit further. We got up to our triple integral equation, which was kind of adding in this engineering demand parameter. That's a phrase Helmut came up with. Going from the intensity to drift and deformation demands, and then to damage. Given the drift, what's the damage? And then to the decision variable. And I wanted just to pause here to say these IM, EDP, DM, DV, if you look around the world now, papers all over use this language. And it started really with their paper here and propagated through the peer researchers, and then people read that and continues to be used. And it's really a great organizing construct. In fact, in the Peer Center, we used it effectively to explain what we were doing to various site review teams that came. Now, I'd just like to touch on a few kind of components of that, the IM, EDP, and so forth. The intensity measure of ground motions. This was an area that Alan Cornell really worked on quite a bit, and with Jack Baker. Looking at if you take ground motions with a ground motion model for a given earthquake magnitude and distance and do a ground motion model, and if you look at the ground motion, some are above it, some are below, you could have a statistic of epsilon, which is how much the variance is at any given period. And to think when we're doing these incremental dynamic analyses and we're scaling up in something in terms of SAT1 at a certain period, that if you take those two ground motions that nominally have the same magnitude and distance, you could see you could scale into the same SA, but the spectral shape is totally different. And Alan coined this phrase, if people are familiar with the KISS, keep it simple, stupid, or stupid, simple. Anyway, Alan, at one of our affiliates meetings with the Bloom Center, the ISS, it's spectral shape, stupid. Stupid being stupid is a good thing. Okay, but this really got into the whole question of record scaling, because at that point we were scaling up records. We weren't using PGA, we were using SAT1, but there was a lot of record-to-record uncertainty. But this began to dissect there's physics underneath these records. They come out randomly from the earthquake, but there's physics driving the structure. So subsequently, Ann mentioned Jack went on to take that concept, develop it further in the conditional spectra that's out there now. And also Eduardo Miranda has worked on a different idea of thinking of an SA average, averaging the SA value over a certain period range. And you could then normalize that by the spectral value and get an SA ratio as a kind of a conditioning factor to characterize the spectral shape. You could also think of earthquake duration. We've done some work, Abby Lyle and some of her students at Colorado have done. The variation of earthquake, the record heavily depends on the magnitude of the rupture. The rupture is continuing, especially when you get to these large subduction type earthquakes. And if you look at the available recorded ground motions and look at what they're their durations are, significant duration. And then if you look at a place like the Pacific Northwest under Cascadia, we have no recorded ground motion. So the thing is, everything we do with recorded ground motions, develop testing protocols in the laboratory and so forth, they're kind of predicated on the kind of earthquakes we've recorded, but thinking of the larger events. And so the idea is you could think of this as duration as yet another adjustment we make to this, quote, intensity measure that could be considered. But in order to pick up that duration, if you're doing it analytically, you need models that capture the cyclic degradation. So some have done this before, some of this current as of 2000 something, without degrading models and see no duration effect. But when you put that duration in, you start to see that effect. And so associated with this, getting this engineering demand parameter, doing the nonlinear analyses is looking carefully, and this is where Helmut's brilliance came in, looking at these different hysteretic models. And the two hysteresis models that are hysteretic that are shown here nominally don't look that different, but you could see the response of the structure is totally different. And Helmut called these happy springs and sad springs. The happy springs are the ones that even though they cyclically degrade, they keep a positive slope. And when you want to solve simultaneous equations, that's a helpful thing. But if you look at real structural components, they get that negative slope, and that's what causes the really damaging effects. And of course, then this has kind of been built into hysteretic models, this IMK model. It's in OpenSeas that quite a few people use, developed. The K is Krawwinkler, Ibarra, Medina, and Krawwinkler that put that model together that we continue to use for a lot of these analyses. Also associated with is trying to characterize the modeling uncertainties through that. And of course, there's ways you could statistically vary different parameters, but then getting correlations between those parameters. Some of it we could infer from laboratory tests. Some of it we have to make a combination of that and judgment. Goes back to Rosenbluth's thought about where you don't have data for something, just don't ignore it. We'll apply some judgment. And mentioning going to damage, it was mentioned both Dan and Bill, some of kind of Keith Porter, and then the important work that Eduardo's done with his students. And to me, I always like this as a great example of looking at damage to gypsum wall partitions, drift, the different damage states. You know, and when you look at a gypsum wall getting damaged, you see a crack, you see a nail pop, you see another nail pop, you see a bigger crack in the wall, and what do you declare to be the damage states? It's really working back from the repair states. You know, at what point you have to replace the whole wall, at what point you could just patch and tape it, you know, that's associated with the outcome of it, that really kind of differentiates these damage measures that we use, because we're looking at the next step. Given the damage measure, how do you repair it? How much does it cost? How much time does it take? And I think it's kind of, and that's for folks in the business, they were doing this, but I think clearly articulating that was important, that we were doing. And of course, we then take these things up to, you know, life safety risk, direct losses, downtime. These are actually terms that I think kind of came out of the HAZUS world, looking at regional modeling. We're carrying it to specific structures. I think, admittedly, when we look at these here, we calculate these. What we do with those, Haresh mentioned this morning, Haresh Shah, you know, how people perceive risk and how they react to it. Are they going to make safer buildings with higher performance? It depends on how you convey that risk to them, and I think that's it remains a challenging area. So Helmut and Alan were really masterful at bringing together the community, and I think they're bringing their corresponding expertise in risk and reliability, the mathematics that Alan brought, and Helmut, his understanding of structural behavior. But they point out that assessing risk is not the end game, it's really changing the future. How do we change our building codes, come up with innovative systems, and so forth. So I'd just like to show a few of the examples that we did in the Peer Center at the time. Mary Camario, who many of you know, is on our research committee, and when we were going through these things, she says, well, you know, guys, okay, you could do these analyses. Why don't you figure out what's the safety we have in our current buildings? You know, and it was like, oh, the light went off. And so we had a benchmarking project, develop at the time a code-conforming reinforced concrete building, and to bring it through this fancy new methodology that we had come up with. And so coming up with an archetype structure, making these detailed computer models, looking at all the experimental data from laboratories coming out, making the model as realistic as possible, doing one of these IDA analyses that we've been talking about through a couple of lectures, you know, taking those intensities at which the collapse occurs, flipping it around and creating a, quote, collapse fragility function, the SA value associated with the probability collapse, building in some modeling uncertainties into that kind of adds the dispersion into those fragility models. And then, of course, you could take that collapse fragility function, probability of collapse versus ground motion intensity, associate it with a seismic hazard curve, which is the likelihood, the mean annual frequency of exceeding that intensity ground motion at a certain site to get kind of an absolute risk. So at the time, this was one of the first serious efforts, I think, to look at a code-conforming building saying, what performance do we get? And then you could start to look at this and say, well, when you say a building's safe, what do you mean? Well, you could go to the maximum considered earthquake level and say, what's the probability of collapse there? Well, it's 5% under the maximum considered earthquake. You could integrate it with the hazard curve, and you could say, get a mean annual frequency, or if you average that out or calculate that out over 50 years, a 0.5% probability of collapse. And then the big question is this acceptable? Actually, someone who worked in the Pearce Center, Peter May, political scientists, say, that's the wrong question, is it acceptable? Because no one can really answer that. It's like, well, how much would it cost to be a little bit more safe or a little bit less safe? That's the best way maybe to address those sort of questions. But so we can't answer that really, or at least as engineers we can't. But in the meantime, we could use this to improve building code provisions. And coincidentally, this work was going on with Pier at the same time the ATC 63 project on collapse prevention, which Charlie Kircher headed up, and we had the opportunity to work with Charlie on that, was going on. We had built a bunch of different archetypes according to the ASC 2005 standard. And we noticed a troubling trend that with taller buildings, the risk of collapse would increase. And someone on the team said, well, didn't you, Kurt, when you designed these buildings, did you use the minimum base shear? And Kurt said, what minimum base shear? It turns out the minimum base shear had been taken out in 2005. It had previously been there in the 2002 ASC 7. So we redesigned some with that minimum base shear. And as a result of that, that minimum base shear came back into the standard and stays there today. So this is just one example of how you could use these sort of tools to kind of tweak the building code provisions to get more consistency. Related projects, and Eduardo and the team worked on this, looking at the losses for these buildings, calculating the losses, but I think some things that came out in some of the studies Eduardo did with students was, there's the risk of collapse, and then there's a risk of damage, non-collapse, and you're going to repair it, but there's also this other risk that you might get so much damage and distortion to a building, it's still standing, but essentially you need to demolish it. And of course, that's a level of loss, that trumps, sorry for that word, that, that whatever the repair cost, so they could start to differentiate those sorts of things. So this is the kind of work that was going on. As I mentioned on the collapse study, this FEMA ATC 63 project, which is FEMA P695, came in the list of course, Charlie led this effort. And you see the other Stanford folks who were there. And it also went into, on the loss side, the more comprehensive analysis into the FEMA P58. I'd like to mention one last study before we wrap up, and this was a little more recent one, where we were enlisted another peer project. We got pulled in and funded by the CEA, who was interested in incentivizing homeowners to do retrofit of the kind of foundation wall, a cripple wall part of your house, to incentivize owners to retrofit that. And Janelle Maffei, I think I saw her before, leads this tremendous program in the CEA to incentivize that, and possibly to alter insurance rates to people if they do that. Now, the plot on the right is showing a lot of the loss data from houses that was collected over the years. Under certain ground motions, house is undamaged, under other, it's 100% loss. If you draw a curve through it, lo and behold, you get an average that looks like the hazardous loss function. So that's good on getting an average loss over an area, but if you're trying to incentivize homeowners to do something with their house, maybe they need to know more details about their house. Is it 1 story, 2 story, stucco, wood siding? Dave Welsh, who's here, ran the zillion of analyses for this, but we took the FEMA P58, detailed OpenSea's computer models. I think we had 115 different archetypes, configurations, and you couldn't do this without developing a computational workflow to automate this process and come up with damage functions. And just to demonstrate, depending on whether, for example, you have a house that has wood siding versus one that has stucco, which is typically a more robust enclosure, what's their collapse risk and how much you could avoid that by retrofitting this small foundation element. Evan Rees was also working on this project and took information like that and translated into diagrams like these on the right to better communicate, you know, like depending what style house you have, depending on where you live in California, that if a, quote, big earthquake, you know, and of course we could characterize that, but, you know, tell people a big earthquake, if it happens, this is how much your loss could be, and then it incentivizes you to think about retrofitting your house. Okay. And I think, you know, going forward, taking this idea of what we're doing building by building to the regional, and this is something in after lunch today, we'll start to go from performance-based of buildings into the regional risk and resilience, but that's kind of the future, if you will. So I'd just like to end by, again, I mentioned this morning, you know, acknowledging the important role that PEER and ATC in particular, the SIM Center, and these federal agencies, we're hoping they're still going to be there supporting this work going into the future. So thanks for your attention.